So let's come to the mechanisms of microstructure evolution. If you have a microstructure like this one here on the top, then the formation of this microstructure is governed by three different areas. First, the thermodynamics provide the energy scale, which tells us when a phase is stable at all. Then the diffusion, like used in Dictra, tells us how fast the transformation takes place. And then there is a third one, which defines the length scale in our system. That's the so-called phase field method, which we are going to explain in a second. The story is that also the local curvature of a solidifying interface influences the equilibrium. So you can imagine soap bubbles where larger soap bubbles vanish on behalf of smaller soap bubbles if they are in contact. So let's come to the phase field method. In order to describe a microstructure, we first need some sort of mathematics which explains us what kind of function describes the microstructure. And actually we define a function called phi, and this function phi is a function of space and time. And for the materials people, it is most easy to interpret the phi as a fraction of a specific phase being present at a spot x and at a time t. So this simple example of a solidification problem, we've got the green areas where the phi takes the value 1, which corresponds to the 100% solid and accordingly 0% liquid. And in the liquid areas, the phi takes the value 0, which is 0% solid and accordingly 100% liquid in this two-phase problem. And then there is a transition between the 0 and the 1, which happens to occur over a diffuse boundary. But actually we are not interested in the static description of a microstructure, but we want to see its dynamic evolution. So we want to know how does the function phi dot look like. To get some impression about the phase field equation, here we have a simplified view, but it's a very instructive view. So in order to understand or to motivate an equation for the phi dot, we can take this equation and in the first approximation we just consider a diffusion type equation where the phi dot is proportional to the nabla square phi. What happens in a diffusion type equation is that an initially sharp interface will smear out and form a flat structure, like you can imagine from an ink droplet dissolving in a liquid. So this is obviously not sufficient to describe an interface in a microstructure because the interface would not be stable. So we need a second term denoted here, which is called the stabilizing term. So please note that this term makes vanish in case in the fraction solid is 1, so that will become a 0. So this term vanishes in the solid. And it also vanishes in the liquid where the fraction solid is 0. And the other interesting story is that here is a change of sign when the fraction solid corresponds to 0.5. So this term somehow counteracts the effects of diffusion, and due to this change of sign I mentioned, we get a situation where we remove the phase fractions in the area where phi is less than 0.5 and get it back up to the hill into the area where phi is bigger than 0.5. So these two terms somehow compete, and the result is a stationary but dynamic interface in dynamic equilibrium. This interface will not move unless there is the third term, which involves a parameter, a factor called delta G. So the delta G already implies that it is a difference, and this is the difference in the bulk free energies between the two phases. If the difference is zero, we will stay with a stationary interface. If the difference is non-zero, then we will have a translation of the interface, a movement of the interface, and the direction of this movement depends on the sign of the delta G. So we either have growth or dissolution, which is depicted here again. So the delta G may be different at any point in space, so itself is a function of space and time. And the delta G actually depends on the local conditions of the external fields, like temperature, concentration, but it may be also elastic strains or electric magnetic fields. So if there is a finite delta G, we will have a phi dot. And if there is a phi dot, then there is release of latent heat, which will influence the thermal field. And if there is a phi dot, we will have release and segregation of solute, which will influence the solutal field. So we've got a set of coupled differential equations where the T goes back into the driving force, into the delta G, and the C goes back into the driving force. And if we couple these set of differential equations, then we can describe the evolution of complex structures in space and time. Like this dendrite here in an aluminum silicon alloy growing in a temperature gradient. What I did not notify you is where does this anisotropy come from. So this dendrite shows a fourfold symmetry, which is not isotropic. And the question is, from where in these equations does anisotropy come from? So let's have a look at the different parameters entering these equations. This delta here, this is the width of the finite thickness interface, and the sigma is the interfacial energy between the two phases, and the mu is the mobility of the interface, which means how does the interface react on a given intercooling. The two parameters sigma and mu may be considered as anisotropic here in this case, just for a two-dimensional case with fourfold anisotropy. These descriptions become more complicated in 3 dimensions. What I showed by now is a phase field model for a simple binary system consisting of 2 phases only, the liquid and the solid. So we have now a phase field model which can describe the evolution of dendrites, but it cannot describe multiphase equilibria because we just had one phase field. And the multiphase field model which we need in order to model technical alloy systems, real alloys with multiple phases, multiple components. So we will need multiple phases multiple phase fields, we need description of multi-component diffusion, and we need something like thermodynamic databases. One concept for multiphase systems has been published first time in 1995, and it has become a quite basis for many other multiphase models. The basic idea of this multiphase field method is to describe or to assign one order parameter or one phase field to each phase. So we've got a fraction liquid wherever there is liquid, we've got a fraction of ferrite wherever there is ferrite, and we've got a fraction of austenite wherever there is austenite. And so what happens is that in thermodynamics we may have a triple point where we've got an equilibrium between ferrite, liquid and austenite at the peritectic temperature. And if we map the phase diagram into a directional solidification situation with hot and cold, then we get a directional growth of the ferrite in the ferrite region, and we've got the triple junction, which is zoomed in here, magnified view, where we've got three phases in coexistence. Please note that wherever the fraction liquid is 1, there may be no ferrite and no austenite. And wherever the ferrite is 1, there may be no liquid and no austenite, and so forth. The concept goes even beyond defining one phase field for each phase, but it also takes into account one phase field for each grain of each phase. That means that we may have several grains of ferrite in a microstructure, for example, grains number 1 to 10, or phase fields number 1 to 10. And the austenite grains then would be, for example, the numbers phase field number 11 to 20, and so on. The model can account for specific boundary and phase boundary properties, like, for example, interfacial energies or interfacial mobilities. And we have the pairwise interaction between each pair of phases and grains, like in the standard phase field. The further concepts are to couple this multiphase method to existing thermodynamic databases and also to take data for diffusion from existing mobility databases. In contrast to the one-dimensional dictra, a multiphase field method can handle the physics of triple junctions, so wetting phenomena and other areas.
Here you see the solidification of a superalloy containing nickel, cobalt, chrome, aluminum, titanium, molybdenum, tantalum and niobium. Hence, there are several phases being simulated by MICRESS. But there is a wide range of applications, such as cast iron, steel, aluminium alloys, magnesium alloys, and even solders.
Let's come to intermediate summary number 3. So what we can do now is all we could do before. For the information on kinetics, we now also can tackle nucleation phenomena, although a certain calibration surely is necessary. But now we also have information on microstructure in 2D and even 3D. We still do not have any information about materials' properties or information of the properties on a component.